Hi, here we are discussing about a project hardware efficient logarithmic floating point multiplier for error tolerant applications. So here in this project we developed and implement a novel logarithmic floating point multiplier tailored for error tolerant applications, leveraging approximate computing technique. The proposed design utilizes simple operators such as adders, multiplexers, entirely avoiding internal multipliers to enhance the hardware efficiency. A significant innovations in our approach in this integrations of the Bohm parallel prefix adder, so replacing with a conventional adders to further reduce the area and power consumptions while maintaining computational accuracy. So this architecture is meticulously designed in Verilog HDLs and synthesized using a Xilinx Zinc FPGA platform. The comprehensive evaluations are conducted to compare the proposed multipliers against the traditional designs. Focusing on the key metrics such as the area, delay and power, the result demonstrates a significant improvement, making our designs an optimal choice for resource constrained computations intensive applications such as JPEG image compressions and neural network training. Now we can verify the paper. So this paper is fully designed for the floating point multiplier for error tolerant applications. So here this is a single precision floating point multiplier with a double strided error distributions architecture. So here we have developed three different architectures of logarithmic multiplication, okay, but here they are not used a normal multiplier for Mantissa, okay. So here, so this is a format of IEEE 754 FP representations. It will be present with this type of format, a sine, exponent and mantissa, okay. So here the logarithmic multiplications 1 and the logarithmic multiplication 2, the equations representation updated here in 9 and 10. As per that we need to create a logarithmic and anti-logarithmic functionalities, okay. And the internal architecture of this method it will be given in figure 4 and figure 5 and figure 6. So here the first part we will be developed with a generic method, so generic circuit architecture for the proposed designs, okay. It will be almost same for the floating point multiplier, normal floating point multiplier, but only thing is the multiplication part we will remove it and the mantissa, okay, and additionally we are added with the logarithmic approximation, anti-logarithmic approximations and addition part, okay. So as per that we need to create architectures and we need to prove the functionality in the Xilinx Zinc FPGA, okay. So here this code we will developed in a Verilog HDL and simulated in Modelism and synthesized in Xilinx Word, okay. So here this is a 32-bit floating point multiplier, okay. First one is a generic circuit architecture, the second one is the circuit design of the first proposed floating point logarithmic multiplier FPLM1, okay. So here the FPLE architectures, the shifting method will be updated here, and this is a logarithmic method and this is an anti-logarithmic method, okay. And the figure 6 also same, okay, but the anti-logarithmic method here they are modified and reduce the logic sizes in the FPLM2, okay. So now we can verify the Verilog HDL coding for these architectures, okay. So first architecture is in generic method, okay. So this one, okay. So here this is a Verilog HDL code, okay. So here the test bench will be updated and this is a single precision architectures, logarithmic, anti-logarithmic, Bohm adder and Bohm 8-bit adder, okay. So here the proposed method we have updated with the Bohm parallel prefix adder instead of the conventional parallel prefix adder to reduce the logic sizes and to increase the speed in the hardware architecture, okay. And this is the logic sizes of the code for FPLM1 and this is a FPLM2 architecture code, okay. So we can't possible to show this code in open, okay. So if you need you can verify it at my website, okay. Here the synthesis report and the simulation report, now we can verify it, okay. So here you can verify the simulation results, okay. So here A input, B input and FP results, okay. So here this one also A input, B input and FP results. So this is a approximation results only, okay. So logarithmic approximations technique only we have used it here, okay. So here this is the inputs and outputs, okay. So here we have run it n times, okay. You can run anywhere, okay. We can analyze it. So here also we can analyze A value, B value and FP results, okay. and this is a simulation result for generic method, and this is a simulation result for FPLM1. Okay, and this is a simulation result for FPLM2. And for the synthesis technique, we have updated in Xilinx Vado. Okay, so here we have used a Zinc 7000 series of FPGA. Okay, and here you can analyze the generic method of LUD 72. Okay, and power consumptions. Okay, so here the schematic. Okay, here you can verify the schematic as per the Verilog HDL code. The first A input, B input come with the logarithmic approximation. Okay, so this is a Mantis method, and the exponent additions will be happen here, A and B. Okay, so this is a 8-bit Bahung adder, and this is a 24-bit Bahung adder. Okay, the logarithmic approximations will be generated using this multiplexers. Okay, and this is a Bahung adder 8-bit architecture. Okay, and this is a Bahung adder for 24-bit architecture. Okay, so here after this additions, we have used anti-logarithmic functionality. So this is a generic method of anti-logarithmic functionality. Okay, with support of the multiplexers and operators. Okay, and this is a exponent normalizations method. After that will be taken the output. Okay, so this is a generic method. Okay, and this is a FPLM method. Okay, so here you can verify the schematic part. Okay, so here this is a same. Okay, logarithmic FP, you can verify the architecture. So here the logarithmic FPLE, after that it will become with adder. Okay, after that anti-logarithmic functionality. Okay, and these architectures, they are used 4 different logic gates. Okay, so they are used the sign bit of MA, MB and MQ. Okay, we are sort out it, and it will be reduce the logic sizes here. Okay, so here okay, and the FPLM2 schematic. Okay, so here you can verify it. So the logarithmic Bahung adder. Okay, and this is a 8-bit Bahung adder. This is an anti-log assessment. Okay, so here this is a multiplexer architectures as per the figure 6. Okay, so this is a totally 3 different architectures. Okay, so this 3 different architectures we have updated in the Vado, and it will be compared it here. Okay, the comparison of single precision logarithmic floating point multiplier using Bahung parallel prefix adder. Okay, so generic method FPLM1, FPLM2. Okay, and the result examples also updated here. Okay, and we have updated a basic document for this project. Title, base paper abstract, and improvement of the project, proposed abstract, existing system, disadvantages, proposed system, advantages, and related notes for this project. Finally come up with literature survey and references. Okay, thank you.